Tēnā koutou katoa, ahi ahi Māori e hoa mā, nau mai, haere mai, kia ora and welcome everyone to today's STARR Talks 2024 session from Resilience to Nature's Challenges. My name is Jenny Steen. I am a Communications Advisor for the Zealand National Science Challenge, and I'm delighted to be hosting you today as we present work from our postgraduate students that we have been funding as part of the challenge. But before we get started, I'd like to settle us in with a karakia. So, kimihia te pō, rangahaua te ao, kia I o rangi, kia I o whenua, ki ngā mato te ariki, ke mata nuku, ke mata rangi, ke reira koe e tānei te waiora. Ko ngā maungaru, ko ngā awa para whenua, he re uta ki tai ki a tangaroa e. Ko koe, ko au, ko taua nei, whiti ao, whiti ora, aramai te toki, haumi e, hui e, tai ki e. Kia ora everyone. So we've got an exciting lineup for you today. We'll be starting off the session with our lightning talks. These will be from our students, so they will each have 5 minutes to present their research projects to you today. These are broken into 3 thematically based sessions: accelerating resilience, hazard, risk and uncertainty. After that session, we'll have a 10-minute break, and then impacts and planning. After that session, we will then separate you out into breakout rooms based on those 3 session themes, where you can then ask the students your questions and have a discussion about their work. You will be automatically assigned to those breakout rooms, but again, this is actually the first time we've tried doing breakout rooms with a live audience. So if there are any problems, I ask for your patience and we will try and sort those out as quickly as we can. After the Q&A session, we will invite you all to come back to the main room, where we will have 15 minutes just to summarise the discussions that took place and to wrap up for the day. If you have any questions or comments at any point, please put them in the chat. If they're questions about presentations, we will address those in the breakout sessions. And just for your notice that we are recording the main session today for the students' presentations, so we can keep a record of those and share them after the fact. So I'll move on to introducing our students. As part of the Resilience Challenge, it's been our great pleasure to support over 120 postgraduate students during the 10 years of our challenge. Our challenge officially ended on the 30th of June, along with the other national science challenges, and we're just kind of in our closeout period where we can do some comms, and we really wanted to give our students one last chance to share their work with each other and with you all. So without further ado, I would like to hand over to our first speaker for the day, who is Manomita from Massey University, and she'll be presenting on communication for supporting civic participation and collective action in disaster reduction. Over to you, Manomita. Thank you.
Thanks, Jenny. So hi, I'm Manomita. I'm from Massey University and I'm working with Julia Becker, Emma Hudson-Doyle and Sarah McBride. So my PhD research focuses on understanding the role of communication in supporting local community actions to reduce disaster risks. So in today's talk, I'll share an overview of my thesis and some of the key findings. So we are all aware that New Zealand faces multiple natural hazards. We also know that the impact of these hazards can be significantly reduced if local communities who are at risk are involved and empowered to reduce their risks, like Chanthujan just informed us earlier. So at an individual level, it involves knowing protective actions like drop, cover and hold and having emergency kits ready. At a community level, it involves collective activities like practicing emergency evacuation drills or creating community response plans, which identifies the resources and skills within the community. Both individual and collective actions are crucial because for some disaster-related problems cannot be solved by individual efforts alone and would require community collaboration. However, in New Zealand, there is currently a gap in understanding this community-level collective actions, and my thesis aimed at addressing this gap. So I had 2 broad research questions. The first was to understand what we mean by civic participation and collective actions in disaster context and how communication can be used to support it. So in my study, I used a mixed methods approach, collecting qualitative data through observations and interviews with emergency management officials, community-based organizations, community members and leaders, and quantitative data through some surveys. And data was collected from 4 study sites, Edgecumbe, Mount Cook in Wellington, Arthur's Pass and Gore from Southland. So with regards to the first research question, we find that collective action occurs currently in 3 main forms as presented in the slide here. They support different activities like identifying evacuation centers or maintaining response equipments, promoting connections and communications. And our findings highlight that the current approach in New Zealand is quite well suited to support spontaneous volunteers post disasters, and thus is helpful to build resilience. However, other forms of collective action, such as tackling environmental factors which cause risks, were largely missing in the DRR space. So we find that the current approach is largely centered around preparedness for response, but there is limited focus on stopping or preventing risk creation. Another aspect of the research was looking at the different factors that influence people's involvement, and we find that factors like having trusted facilitators, community conversations, and providing institutional support is crucial. And at the individual level, motivational factors, of course, we have the expected factors like risk perception and sense of responsibility. However, an interesting element was that the social aspect of participation, where we found that many people joined and continued because they wanted to know others and make friends. So when we are looking at community participation, looking beyond risk and identifying how we can bring some added values in community actions might be beneficial. To address the second question regarding communication's role, so we used a communication ecology perspective. This perspective views people as part of networks connected to various actors like friends, neighbors, community organizations, local media, and government agencies. It leverages these networks, especially the informal connections, to disseminate disaster and risk information, foster a sense of community, and promote civic participation and collective action. So we mapped this communication network and identified the actors, the resources, the contextual factors that influences disaster-related conversations and engagement in these networks. We find that communication flows quite differently in different communities depending on their hazard experiences and demographic characteristics, and unpack some of these nuances. We also look at the role of social networking websites like Facebook in the process. Additionally, we're interested in understanding the narratives and conversations happening in these networks. So we explored some of the themes that are dominant, like connection and care, collective efficacy, and how they are supporting participation and what their problems are. So the findings have several theoretical and practical implications, but some key takeaways are: firstly, it's important to identify and work with the existing networks and organizations within a community, and then considering value addition, because often people don't engage only for reducing risks, but they also engage for spending time with friends. So thinking about these broader linkages. While strengths-based approaches that utilize community resources is helpful, communities often need institutional support, and we should think about providing that whenever that's required. And adopting a holistic view of emergency management, considering the cross-sectoral linkages with environmental factors, developmental processes, etc. So this is a very, very brief overview of my research. Thank you for listening, and that is my email ID. So I would be very happy to have a chat if you have any questions or suggestions. Thank you.
Wonderful. Thank you so much, Manomita. I'm sure there will be lots of questions in the breakout session later about just exactly what things people can do to implement those key takeaways of yours. Thank you so much. It's now my pleasure to hand over to Chanthujan Chandrakumar, also from the Massey University Joint Centre for Disaster Research, who'll be presenting Shake It Up, How Communities and Low-Cost Tech Can Beat Earthquakes. Over to you, Chanthujan.
Perfect. Hello everyone, I'm Chanthujan Chandrakumar, a PhD student from Joint Centre for Disaster Research, Massey University, Wellington. Today I'm going to take you on a journey through a groundbreaking approach to earthquake preparedness in Aotearoa, New Zealand. Before jumping into my research, I would like to acknowledge my awesome supervisors and my funders who funded my research. Cool. As we all know, there's no better love story than earthquakes and New Zealand. The left-hand side figure shows the history of earthquakes that happened during the past 10 years in the history. So as researchers, what we have been doing to reduce the impact caused by an earthquake? The first thing that comes to my mind is teaching people about earthquake preparedness, which is very important. You know what? We can add one more thing to the list. Implementing an earthquake early warning system. So what is exactly an earthquake early warning system? To answer that, we need to look into earthquakes. As you can see from the figure, during an earthquake, mainly two waves are generated. First, the P waves, then the destructive S waves. An earthquake early warning system detects one of these waves during an earthquake and alerts people before the shaking arrives. Generally, an earthquake early warning system generates warning times in seconds. You know what? Even seconds saved many lives during an earthquake. So, you all would be wondering, why there is no earthquake early warning system in New Zealand? So, one of the reasons for not having an earthquake early warning system in the country is that it's super expensive. Even a single sensor would cost more than 10,000 US dollars. So, let's jump into my research. During my PhD, I'm trying to fill the gap of not having an earthquake early warning system by implementing a low-cost network with community engagement. Yeah, you heard it correct. Let's see how I'm going to do that. I followed 4 steps to achieve my goal. My first step is choosing low-cost ground motion sensors instead of expensive ones. Meet my friend, Mr. Raspberry Sheikh, the sensor I'm using in my network. He cost only 600 US dollars. And you know what? He is more than enough for earthquake early warning. The second big step in my research is community engagement. I delivered these sensors to the general public of Wellington and asked them to install the sensors at their household. Through this community engagement, I achieved 2 main objectives. The first one is the infrastructure for installing these sensors are completely free. I don't need to pay for the electricity, or I don't need to pay for the broadband. And also, I had a great opportunity to talk to people about earthquake early warning and about earthquake preparedness. Here comes the third part and my novel part of my research. In my network, the sensors talk to each other directly. Letting the sensors talk directly without any centralized computer make the networks very fast. And there's no centralized computer, which means the implementation of the network is even cheaper. As you can see, when the first sensor detects an earthquake, he shouts out to the second one. When both confirm that it has an earthquake, then the alerting device will generate an alert. So the last part of my research, implementing PLUM. No, not this PLUM. PLUM is an earthquake early warning algorithm which has shown great accuracy and reliability in generating alerts in Japan. So I adapted the PLUM algorithm for my network. But the main limitation of PLUM is it detects earthquakes using S waves most of the time. As I mentioned earlier, S waves comes after P waves, so it reduces the warning time. So I modified the PLUM algorithm for New Zealand to detect P wave by integrating a P wave detection algorithm into it. The results showed that my approach increases the warning time without compromising the accuracy. Here comes my groundbreaking results. As of now, I have implemented a community-engaged, low-cost experimental earthquake early warning network in the Wellington region. There are more than 40 sensors running all the time to detect an earthquake. The recent earthquake happened on 6th of July showed that I can give a warning time up to 10 seconds for the Wellington community. So, we all know that if we feel shaking in New Zealand, we need to drop, cover and hold. But with my research, you can do drop, cover and hold even before you feel the shaking. Just wait for my alert. Thank you.
Wonderful. Thank you so much, Chanthujan. Very exciting to see that we might be able to give some people a few seconds warning prior to earthquakes in New Zealand, hopefully soon. It's now my pleasure to hand over to Lydia Michaela Mairereki from Lincoln University, who will be presenting Dimensions of Visitor Resilience to Natural Hazards in Conservation Areas of New Zealand.
Hi, Jenny. Sorry, I don't know what happened. I went all gray You couldn't unmute, so thank you for re-enabling that somehow. So my name is Lydia Michaela-Mainadiki. I'm from Lincoln University. My topic that I'm going to talk to you guys today is about dimensions of visitor resilience to natural hazards in conservation areas of New Zealand. So I'm funded through the Resilience to Nature's Challenges National Science Challenge, and also through Lincoln University. So just to start off, I want you to take a moment to look at this picture. There's a woman sitting, it looks very idyllic. She's enjoying the sunset, looks very relaxing. But what if this picture is actually telling us a different story? What if this woman is sitting here because she got lost and she didn't bring a map and she didn't bring a GPS, and she's not sure where to go, and the sun is going down, it's taken a lot longer than she thought it would? Or what if this woman thought, I'm going to stay the night in a hut, but she didn't really check the weather. The river that she needed to cross is too high and it's flooded. And so she's stuck. So she can't get to a hut, and she didn't bring a backup tent. So these scenarios are not unlikely. We know that about 80% of people who live in New Zealand visit a conservation area at least once a year. We also know that our conservation areas are really popular destinations for our international visitors. And our conservation areas are also dynamic biophysical environments that are subject to natural hazards. So severe weather, we could have flooding, some landslides, earthquakes, that's all present in our conservation areas. So to investigate the question of what is visitor resilience to natural hazards, I took a social ecological systems approach. And what a social ecological system is really is just the coupling of human and environmental elements, and you're looking at that across different scales, so local, regional, national, and international. So the term resilience has been used in a lot of different ways and in a lot of different contexts. I used a mixed methodology to investigate what visitor resilience might mean. So I did a quantitative survey that went out online to New Zealand-based outdoor recreation groups. I also did qualitative interviews with stakeholders from the Department of Conservation, some outdoor safety groups, and others. And then I also did qualitative interviews with visitors that was recruited from the survey. And so there are a lot of findings that I could share, but I'm going to share two high-level diagrams and just talk to you a little bit about those. And if you have more detailed questions, I'm happy to answer those in the breakout room or via email. So this first one is, what does it mean for a visitor to be resilient? What is resilient composed of? So what I found is that resilience is actually another way of saying awareness, preparedness, and adaptability. And that is a combination of these at least 6 factors. So this figure is still under revision. So if you have feedback, I'm happy to hear it. So the 6 areas are where you come from, where you go, who you are, who you go with, what you take, and how you prepare. So those 6 areas affect how resilient or how aware, prepared, and adaptable a visitor is for encountering natural hazards. So I'll just give you a quick example. So the where you come from. So we know from different research that some visitors who come from urban areas have not been exposed to the natural hazards or even the weather conditions that they will experience when they're out recreating in some of New Zealand's areas. And so because where they come from is so different from where they are going, their ability to understand, their experiential knowledge of what they're going to encounter is a bit challenging for them. So this is the final figure that I'll discuss just a little bit. And so what this research has revealed for me, and I hope for others, is that when people are coming to recreate in New Zealand's conservation areas, they come from a social ecological system of origin. So they come from a place that's a combination of social, natural, technical, infrastructure. All of those things create the environment that they come from, and that shapes their expectations and their expectations of what they're going to experience. And then they come to our conservation areas, and that conservation may be very similar or maybe very different from their social ecological system of origin. And so how the differences and the similarities between those two different places and how have a large influence on how prepared or how aware or how adaptable somebody might be. So that's all for me. Thank you very much, Jenny.
Thank you so much, Lydia. Wonderful presentation. And yeah, I guess growing up in New Zealand, a lot of us take for granted that we feel we know the environment and the hazards, and we forget that actually people coming from other places, I don't even know what they're not aware of, because they come from such a different place in a different context. So really important work. Thank you so much. So I'd now like to transition into our next session. That was our Accelerating Resilience session. And then we will be moving on to a new topic now and hearing from 4 students in hazard risks and uncertainty. So I would like to hand over to Jade Humphrey from the University of Canterbury, who will be presenting insights into complex earthquakes in central New Zealand. Over to you, Jade.
Kia ora, my name is Jade and I'm a member of the Earthquake and Tsunami team. Today I'll be talking about what future large earthquakes may look like in central New Zealand. I'd like to take the time to thank the Resilience Nature's Challenges program that has enabled me and many others to complete their PhD research. So how do we currently forecast large earthquakes? Well, we typically rely on information collected from past earthquakes. However, these data sets have limitations. Our written record is less than 200 years long, and our instrumental record is even shorter. We also use paleo-earthquake techniques, which provide us with data for about 10% of our known active faults. Because our records of large earthquakes are short and incomplete, we are uncertain about what fault interactions are possible, with events like the 2016 Kaikoura earthquake highlighting this challenge. We also, thankfully, have not had a good example of the Hikurangi subduction zone rupture, and we are unsure how shallower upper plate faults like the Wellington Fault will respond. Our research team has been using programs that generate long records of simulated earthquakes to understand future events and many of their associated hazards. Govinda and Mika will introduce the RSQ Sim earthquake simulator shortly, and I will briefly discuss some of my results using the Central New Zealand model shown here. Central New Zealand has been a great location to research future large earthquakes for many reasons, including its short history of complex and damaging earthquakes like the 2016 Kaikoura and 1855 Wairarapa earthquakes. It has a high seismic risk, which has been demonstrated historically, and consequently has a relatively good paleo-earthquake record. As I mentioned, we've just generated an earthquake simulator for the region. So yeah, during my PhD, I've been comparing earthquake timings of 3 key upper plate faults, and these are the Wairarapa, Wellington, and the Aotearoa faults, and comparing them to the Hikurangi subduction zone off the east coast, to help better understand the interactions of these faults during large earthquakes. So how could these key faults rupture during large earthquakes? We may have an earthquake where either an upper plate fault, like the Wairarapa fault, or the Hikurangi subduction zone ruptures by itself. While in more complex scenarios on the bottom, we may see multiple upper plate faults, like the Wairarapa and Wellington fault, rupture together, or even a combination of these upper plate faults rupture with the Hikurangi subduction zone. We are interested in the Hikurangi earthquakes as these ruptures are often associated with additional hazards like tsunami and different ground motions. It is also important to note that stress transfer between faults could also result in a series of earthquakes. So the series of earthquakes could occur over a couple of days to many years, similar to that of the Christchurch earthquake sequence. And these sequences have their own associated hazards. So I've been using a few data sets during my PhD. I mentioned some of the historical records, but it's too short on its own. So I'm going to move on to paleo-earthquake timings. So this plot is the result of lots of interrogation and revision of paleo-earthquake timings for the key faults I've discussed. The curves show the annual probability of an earthquake occurring over the last 5,500 calibrated years. So on the y-axis, 0 is 1950 AD, and the plot gets older upwards. The peaks of the curves represent the greatest probability of an earthquake occurring. So if we focus on those peaks, we can see some consistency across the key faults, which suggests there is some of the earthquakes are clustered in time. It is difficult to tell due to the resolution of our data if the clustered earthquakes are occurring at the same time, like the Waikato earthquake, or as a series of earthquakes closely spaced in time, like the Christchurch earthquakes. However, at least 50% of the earthquakes appear to be complex, kind of like our scenarios here. We're now going to jump into the earthquake simulator. And if we look at the earthquake simulator, we see many examples of our 4 rupture scenarios with different combinations of faults involved. If we start filtering the catalogue for events that are more hazardous, so they're greater than magnitude 7 and rupture to the ground surface, we can see that the complex events shown in purple and pink here, so multiple faults involved, make up about 75% of our total events. So in conclusion, I'm running out of time, but we have evidence of large earthquakes in all 4 of our scenarios, and the complex earthquakes seem very common in both the paleo earthquake and RSQ sim, and it's really important to consider these co-ruptures, especially of Hikurangi and upweight faults in seismic hazard models. Awesome, thank you.
Wonderful. Thank you so much, Jade. It's been really interesting the last few years to see the progression, particularly in the public communication of earthquake science space, from an earthquake is happening on one fault to it can happen on multiple faults at the same time. So great to see you working on that and developing the history there. So I'd now like to hand over to our next speaker, who is Govinda Prasad Niroula from the University of Otago, who will be presenting on comparison of seismic hazard estimates from physics-based earthquake rupture simulator with the New Zealand National Seismic Hazard Model 2022. Over to you, Govinda.
Prasad Niroula. I'm a PhD student at University of Otago. Professor Mark Sterling, Jack Williams, and Matthew are my professor, and I would like to thank GNS Science, RNC2 for the funding. And so today I'm going to present about the comparison of seismic hazard estimates from the physics-based earthquake simulator RSQ sim with the recently developed New Zealand National Seismic Hazard model. So as we know, in New Zealand, we have in total of around 800 active faults. The figure on the left-hand side shows the 3D geometry of the active faults in the New Zealand. And on the right-hand side, we see the slip rates of these faults. So these are the National Seismic Hazard Model 2022 and the RSQ sim, they both have used the same model. So here in my presentation, I'm comparing the hazard estimates from the earthquake simulator RSQ sim with the New Zealand National Seismic Hazard Model 2022. What is an earthquake simulator? Basically, earthquake simulators are a physics-based computer model that takes the fault geometry, slip rate, and friction properties as an input, and it generates the earthquakes for 100,000 of years. And the question is, why we need the 100,000 of years earthquake? To forecast the probabilistic seismic hazard or the ground shaking, we need the earthquake records of 100,000 years long. So, but in New Zealand, we have around 200 years of historical records and few thousand years of paleoseismic record. We believe that these simulators can fill the gap that historical and paleoseismic earthquake records have, and we can get the very precise seismic hazard map in the future. But before doing that, the output from this simulator must be tested against the well-established method or the observations. So here I'm comparing the seismicity rate, seismic movement, and the seismic hazard estimates from the RSQ sim earthquakes with the recently developed New Zealand National Seismic Hazard Model. Here on the left-hand side, we can see the earthquake distribution, epicentral distribution of earthquakes from the RSQ sim, and on the right-hand side, we can see the ruptures from the RSQ sim corresponding to these epicenter. So here we see in the Otago region, the simulator has generated very few earthquakes, but in the Alpine, Marlborough, and the Wellington regions, the number of earthquakes are quite high. So here, now what I did is I compare the seismicity rates from the simulator and with the New Zealand National Seismic Hazard Model. The black line shows the number of earthquakes per year greater than certain magnitude estimated by the National Seismic Hazard Model, and the red line shows the earthquake rates from the RSQ simulator. Here we can see that the rate from the RSQ sim are within the National Seismic Hazard Model boundary distribution. So it means we can say that the RSQ is generating the earthquake that is in agreement with the National Seismic Hazard Model. And if we compare the seismic movement rate, we can see that the seismic movement rate is very close to the median. And so next what I did is, using all the rupture sets, I prepared the probabilistic seismic hazard map or the ground intensity map in terms of PGA. Here, this figure shows the hazard from the RSQ sim, and the next figure, this figure shows the hazard from the New Zealand National Seismic Hazard Model, and the rest two figures shows, the other figure shows the difference in PGA. Here, in both the model, we can see that the higher hazards are along the Alpine Marble Fault System and the Hikurangi subduction zone, and low hazard in the Wellington region, and where the fault slips are very low. But if we look the PGA difference in terms of G, we can see that the Hikurangi zone has the higher hazard differences, but which the value here is about 0.4 G. The difference in PGA is around 0.4 G. But in terms of percentage, if we look, we can see the discrepancy between the simulator and the National Seismic Hazard Model is on the region of low slip rate faults and on the Hikurangi subduction zone. So further, what I did is I compare the site-wise comparison, how the simulator and the National Seismic Hazard compare for each site. So to do that, first I took all the sites on the South Island and the North Island. This shows the South PGA from the simulator versus the National Seismic Hazard Model on the South Island. Here we can see the very good correlation with the National Seismic Hazard Model. The x-axis shows the PGA from the National Seismic Hazard Model and the y-axis from the simulator. But in the South Island, we can see the discrepancy is quite high as compared to the South Island. And on the South Island, only the crustal fault accommodates the plate deformation, while on the North Island, the crustal fault and the Hikurangi subduction, they both accommodate the plate deformation, and the joint rupture between the Hikurangi subduction interface and the crustal faults are the cause of the main discrepancy with the New Zealand National Seismic Hazard Model. Further, I try to explore the model and try to see how the hazard curves compare in the region where there is a high discrepancy in the seismic hazard value. Here in the Dunedin, we can see the discrepancy is quite high, but in terms of hazard, we see that the hazard curve from the simulator lies within the NSHM distribution. So other reason, like if you look in the Wellington, it matches well with the median value, and there is not more significant differences. It means hazard curve from the RSQ sim lies within the 2022 National Seismic Hazard Model. So in conclusion, we can say that we can use the simulator to produce the earthquake rates and the hazard maps that are very comparable to the New Zealand National Seismic Hazard Model. So overall, we can say that simulator is doing a good job when we compare it with the seismic hazard maps. Thank you.
Wonderful. Thank you so much, Govinda. And apologies there for anyone who had trouble with Govinda's slides advancing. It appears there is a setting that enables us to control that each individually ourselves. So we'll try and fix that issue. But in the meantime, I'd like to introduce our next speaker, who is Yi-Wun Mika Liao from GNS Science and the University of Canterbury. So Mika, over to you. Mika will be presenting earthquake cycle modelling for the Hikurangi-Kermadec and Tonga-Vanuatu subduction zones. Kia ora, Mika, over to you.
Kia ora koutou, I'm Mika. My topic today is earthquake cycle modeling for Hikurangi-Kermadec and Tonga-Vanuatu subduction zones. So instead of using the traditional way to assess seismic hazard model, hazard model will now try to use physics-based simulations for the earthquake rupture models. So all you have to do is just input the fault geometry and the initial stress and frictional properties to multi-cycle rupture simulator like what we're using RSQ, and then you will get the long-term synthetic earthquake catalog, and it can be tens or hundreds thousand years, and with the physics-based earthquake rupture models. So like the earthquake catalog Jade and Govinda mentioned earlier. But in these models, they only use a uniform initial stress for the entire fault plane. That will make the simulator generate a lot of generic earthquake rupture models like these three here. So we might miss the complexity of earthquake ruptures in our hazard models, but this is very essential to the local scale seismic and tsunami hazard assessment. To solve this problem, we proposed three initial stress models. So the first one is homogeneous stress model. This is the same idea as the previous models, a uniform value for the entire fault. And the second one is the heterogeneous stress model. The stress is calculated from 4 reactivation equations. And so the stress will increase along the depths, like the blue lines here. And then we also add the brittle ductile transition into our stress model. So the stress will increase along the depths and start to decrease after transition depths, which is 25 kilometers here. Another parameter we're testing here is one of the frictional properties, B minus A. And this is associated with the energy release during earthquake rupture. So to test this, we fix A at 0.001 and then vary B from 0.04 to 0.015. And as you can see the result here in the magnitude time distribution, the homogeneous stress model tend to have some gaps at some magnitude range. So it's not very smoothly distributed. And you can also see this in the magnitude frequency distribution. So we compare our synthetic catalogs to the real earthquake catalog for Hikurangi-Kermadec subduction interface. So it's the black line here, and the color lines are the synthetic catalog. So you can see there are deviations between the instrumental catalog and the synthetic catalog from the homogeneous stress model. In contrast, the heterogeneous stress model, the result from the heterogeneous stress model or the brittle ductile transition model, we have more like a smoother distribution along the magnitude, and also the magnitude frequency distribution match the instrumental catalog better than the homogeneous stress model, especially for those models with B of 0.004 and 0.03, so the orange and green lines here. And it's the same in the result of the brittle ductile transition model. And for the earthquake rupture models, so we mentioned before, the homogeneous stress models tend to generate this kind of generic earthquake rupture models. But if we add heterogeneities into our initial stress, then we will have a lot more complexity and varieties in our earthquake rupture models. And for the Tonga-Vanuatu subduction zone, we adapt the heterogeneous stress distribution to this subduction zone. And then we focus on the change of coupling on the subduction zone more here. So we have a uniform coupling and variable coupling. From the result of Vanuatu, we can see the variable coupling model tend to generate more earthquake with magnitude larger than 7. And for the Tonga, because we don't have much lateral variation on the coupling distribution, so the result from the variable coupling just have a systematically it's systematically lower than the constant coupling. And that's it. Thank you.
Thank you so much, Mika. It was a real insight, particularly for non-technical people such as myself, into the complexity that goes into our understanding of how earthquakes are caused, but also how they propagate. So thank you so much. So now I'd like to hand over to our last speaker in this Hazard and Risk and Uncertainty session, Annal Dhungana from Massey University's Joint Centre for Disaster Research, who'll be presenting Advancing Uncertainty Communication for Disaster Risk Management, the Uncertainty Doughnut Framework. Over to you, Annal.
Hi. Hi. Before I start, I'd like to take you to three different disaster events, one from Japan and two from New Zealand. Among many reasons, the most important discussion is like why these events are discussed. Have you ever thought about it? The most important discussion that comes is like how are scientists and science unable to forecast and the unprecedented events of these impacts? The easy answer is because there's a lot of uncertainties in scientific models that we develop and use, which raises the difficult question. Why are then uncertainties not communicated then? Hi. Hi, I'm Annal Dhungana, PhD student at Massey University with an awesome team of supervisors here. So in my research, I researched that difficult question. Why is so difficult to communicate uncertainties then? Not only I researched why, I came up with the idea of uncertainty doughnut to communicate uncertainties. I'll come to this later in my slide. Before, let's see what we know. What scientific models are there? There are many scientific models that are used, including the fellow like students also discussed about National Seismic Hazard model. One of the model is that. So there are a lot of scientific models that are used. So how uncertainties are communicated currently? You can say uncertainty cone, uncertainty fan graph, and uncertainty curves. These are the ways uncertainties are communicated currently. You must have noticed that these communication mechanisms are very technical and are very much driven by scientists' view. However, literature suggests that these methods are unable to communicate the full scope of uncertainties. They are not helping decision makers utilize uncertainty information in decision making. So, to understand the views of decision makers, I conducted 15 in-depth interviews. I also 17 in-depth interview with scientists during my research, during my first phase of my PhD. Then I come up with this idea of uncertainty doughnut. I analyzed the data from the interviews and came up with this idea of uncertainty doughnut. Then I further validated this uncertainty doughnut through 13 different interviews and 2 focus group discussions. So let's talk about what's uncertainty doughnut then. This is a framework, prioritizations, and visualization tool, all 3 in one. Uncertainty framework, as you can see, is divided into 4 main components: uncertainty source as data, uncertainty due to explicitization of science, uncertainty source as model processing, and uncertainty source at output presentation. As you can see, they are visualized using the surface of the doughnut, whereas the core of the doughnut is represented by deep uncertainty, which cannot be identified, rather they can only be acknowledged. These small boxes represents the unique uncertainty sources, where the size of this box represents its contribution to overall uncertainty of scientific modeling. Bigger the size of the box, bigger its contribution towards overall uncertainty. And that's how we prioritize. This framework and prioritization are visualized using uncertainty doughnut, as you can see here. I can talk about why uncertainty doughnut for another 15 minutes. However, we have just limited time. So I just want to say that this is the first ever 3D visualization of uncertainty framework for scientific models. So let's see how is it used then. For example, if scientists working on flood inundation modeling, traditionally what's being done is they communicate uncertainties in flood height, putting some confidence intervals, plus, minus, and that. Now they can interactively communicate using this visualization tool and say, in generating this flood height, while using this model, these are the potential source of uncertainty in our inundation model. And this source A, as you can see here, in model processing is the most significant contributor of uncertainty. And what will happen then is this leads to a discussion where decision maker can ask questions and initiate discussion about uncertainty. And then decision maker can utilize those uncertainty information in their decision making. I'll end it here and ask you all if you have any questions, like that. They're like in the side that scientists are asking decision makers any questions, and decision makers are asking any questions to the scientists in regard to the uncertainty. Thank you.
Thank you so much, Annal. Yes, uncertainty is a big one in research, and how to communicate that and start those conversations so that people can understand that, you know, there's not always one exact answer, that there is a range of potential options. So thank you so much. That brings us to the end of the hazard, risks and uncertainty session. Please go away, make a cuppa, have a break for 10 minutes, and we will start the next session at 1:10. Thank you so much. Welcome back, everyone. We will get underway with our third lightning talk session for today, impacts and planning. So we have 4 students who will be presenting on their research on the impacts of natural hazards and how we can better plan and prepare for those. So to kick us off for this session, I'm delighted to introduce Thomas Wallace of the University of Canterbury, who'll be presenting Understanding Dam-Stopbank Interactions During Flooding. Over to you, Thomas.
Cool. Hi, hello. I'm Thomas. I'm a student at the University of Canterbury, and today I'll be presenting a very quick overview of part of my PhD research titled Understanding Systemic Flood Risk in Dams and Levees. So floods are New Zealand's most frequent and damaging natural hazard. Now, we have a range of ways of protecting against floods, but today I'd like to focus on our dams and stop banks. So within New Zealand, something that quite surprised me when I started this research was just how many of these structures we have. Within New Zealand, we have over 3,000 dams and over 5,000 kilometres of stop bank. And I think it's important to recognise that when they are in the same river, they actually form a system. So a dam is able to store floodwater, so it can be more slowly released after the event, reducing the flow downstream. And this impacts the amount of basically loading that these stop banks have to contain, increasing sort of the safety that they can provide. However, understanding dam-levee interactions at a system level is a critical research gap, and it's often overlooked. A lot of the research on the cascading consequences focuses on multiple dams failing. So one dam fails, releases water, causing another dam to fail. It doesn't tend to look at how dam operation affects the amount of flood water that's released, as well as what impacts levee breaching have. And so this means that by not considering these cascading consequences, they're overlooked, and so they don't factor into our risk analyses. So with this in mind, this project aimed to investigate how levee breaching and dam operation affected cascading consequences. Ultimately, so we could develop some recommendations. So this actually kind of comes at the end of my project. I've just handed in my thesis. Broadly speaking, it can kind of be broken down into 3 topics. We have the dam operation, where within a flood model, we have 4 target catchments, where by varying the amount of pre-releases and the dam's initial level, we came up with a wide range of dam operation scenarios and the outflows from these. But today we'll just be focusing on the maximum dam outflow, the median dam outflow, and the minimum dam outflow. And this sort of attempts to represent the operation that could happen. And then also we focused on levee breaching. We came up with a method for doing that within HECRAS. And so by combining these 2, we hope to analyze the cascading consequences. So this is what we did. Within HECRAS, we modeled some flood simulations. We took as I kind of said, the best case dam operation scenario, which is shown by the sort of like lighter orange. The medium case dam operation scenario is sort of the darker orange, and the red is our worst case scenario dam operation. And so these are our four catchments. We have the Taylor, the Maitai, Apua, and the Rangataiki. And then you can see with and without stop bank breaching. And so what you can see here is both the dam operation and the levee breaching significantly affect the flood pattern. And so from this, we looked at how the dam operation affects the levee loading. So on the left-hand side, you can see that, if the Taylor Dam was operated at its best, about 35% of the stop bank length reaches sort of the assigned breaching threshold. Unfortunately, don't have time to get to it, but essentially water reached 35% of the stop bank length had water reaching halfway up in the best case scenario, and in the worst case scenario, closer to 70%. So what this shows us is that dam operation does quantitatively affect the loading on the stop banks. From this, we then looked at the losses using those flood maps, and we see that in our best case scenario, so this is our best case dam operation with no breaches, we saw that in the Taylor catchment, for example, there were very few losses. However, in our worst case scenario, with our worst dam operation and levee breaching, we saw those losses increase. And across all the catchments, there was at least a 950% increase in the losses between best case scenario and worst case scenario. And I think it's also interesting to note here that as our dam operation deteriorates, we're more likely to have higher loads and more likely to experience levee breaching. We can also use this to find our critical sections along our stop bank. So we have the stop bank length here, and we can see that a breach on the true left causes more losses than a breach on the true right. And so this helps us find our critical sections to, reinforce or monitor during a flood event. And for the sake of completion, we did this for all our other catchments. So very short presentation, but in summary, we looked at a method for quantitatively assessing the cascading consequences of how dam operation affects levee loading and the losses from those breaches. We saw that dam operation does affect the amount of stop bank that reaches the breaching threshold that we assigned, and we saw that there was at least a 950% increase in losses between best case and worst case scenarios, and that the critical sections of stop bank didn't necessarily align with townships. I just want to say a massive thank you to everybody who's helped me on this journey, in particular to RNC providing such a good community and fostering such a nice research environment, as well as the University of Canterbury and the councils who have provided data and supported this project, and to my supervisors, Tom Logan, Kelly Crawford-Flatt, and Matthew Wilson. Thank you very much. Cheers.
Thank you so much, Thomas, and for the acknowledgement on behalf of RNC and all your other contributors and supervisors. I'm sure you will have many questions from people working in council, keen to hear more. Thank you. I will now introduce our next speaker, who is Joshua Sargent from the University of Waikato, who will be presenting Unravelling the Entwined Relationship of Coastal Flooding and Farms. Over to you, Joshua. We can see your slides. Perfect.
Awesome. I first want to thank RNC and especially my supervisory panel, and including those both at the University of Waikato and NIWA. All right, so the basis is that there is a need for more coastal rural resilience models. There are lots of models that are designed for coastal urban systems, and there are lots of models designed for inland rural systems. However, coastal rural resilience in regards to flooding is a unique kind of category. So in choosing the Hauraki Plains, which has a history of flooding, will be impacted by sea level rise and land subsidence, and is a agricultural center for the Waikato, was exploring farm level resilience with a social hydrological approach. So a social hydrological approach can be done a couple different ways. My model that I developed it looks at it from a systems dynamics perspective, which largely means that like yarn, all of these things are entwined together. And each of these variables are kind of combined in a series of 10 equations that that operate within the model. They're driven by both measured tide gauge water level time series, as well as a series of synthetic storm scenarios to kind of explore how the model would react to storm surge, storm delay, and storm clustering. So some of the key findings from this research is that the current infrastructure seems to be well established, but maintenance is a key part. The model had to be run with a reduced stop bank heights to actually trigger some of the flooding events. When those flooding events occurred, it started to trigger resilience in the system. So a very important thing is the when floods occur, in addition to where floods occur. A flooding event that impacts the system earlier on is actually more beneficial for the system than later on. And some of the characteristics of this flooding, actually, interestingly, occur more so with lower and higher storm surge scenarios, where a moderate storm surge seems to be an adequate challenge for the system that builds resilience without overwhelming the farms and the agricultural operations in the region. So a few kind of further model applications is exploring a element of seasonality. So rural systems operate on a somewhat well-known, this is the season for pasture growth, this is the season for calving, and those important elements are, they modify the flood impact. So that needs to be further explored, as well as kind of exploring the use of this model with dynamic adaptive pathway planning, such that decision making can be done at different, can change over time. And just one little thing is to share is that the Waikato Regional Council is currently assessing the stop banks for their decay rates, so how they're kind of how they need to be maintained, and infrastructure projects are moving forward in the region, and the results of their work would also further improve the model.
Wonderful. Thank you, Joshua. And congratulations on your project also. Now I'd like to introduce our next speaker, who is Muizz Shah of the University of Auckland, who will be presenting ensemble study of Cyclone Gabrielle wind speeds over Auckland City. Over to you, Muizz.
Thank you. I hope you can all hear me. Good afternoon. My name is Muizz, and I'm a PhD student from the University of Auckland. So today I'll be presenting on our ensemble study of Cyclone Gabrielle wind speeds over Auckland. This is just a snippet of some of the work my supervisors and I have been doing, but nonetheless, we're very thrilled to share it with you today. So to get started, some background information on Cyclone Gabrielle. The storm made landfall at New Zealand on 13th of Feb last year. With it, it brought severe wind speeds, torrential rain, and storm surge. And over the course of the storm's period, there was an estimated damage cost of about 13 billion New Zealand dollars. But we're looking at Cyclone Gabrielle near Auckland. And to do this, we looked at NIWA's reanalysis of the storm. The amount of data was abundant, so we ran a time history of the storm around Auckland, and we determined a maximum wind speed about 21 kilometers an hour, which is roughly 21 meters per second, which is roughly 75 kilometers an hour, in front of Auckland at a doorstep, really, around 8 p.m. on 13th of Feb. So once we determined just the situation of the storm at Auckland, we then looked at Auckland two different forms. So on the left, you're seeing Auckland as just the terrain, and on the right, you're seeing the CBD's tallest buildings. Now, the solid red box shows where the tall buildings are, and then the dash red extension behind it is the extension of the CBD itself. From the image on the left, you can see that Auckland is very inhomogeneous in its terrain. It's very complex. There's a lot of hills, there's a lot of gullies, and if you've ever been to the city, you know there's some water there as well. So to actually look at the effect of the terrain, which undoubtedly it does have an effect on any approaching wind speed towards the city, for this presentation, we're only going to look at two hills. Now, both the hills are just under the green dashed arrows, but one is from the east, which is 90 degrees, and the other one is from the west. So to look at the effect of these two hills on the Cyclone Gabrielle wind speeds approaching the CBD, the tall buildings, we tested those two hills in the wind tunnel. And so figure A shows the effect of that close proximity hill from the west to 70 degrees. And so location 1 to location 4, we measured the change of wind speeds around the hill, over the hill. Location 4 is the location closest to the CBD, which is just to its right. And what we noticed is that, well, what we measured was the hill actually causes the wind speed to slow down. Now, this isn't always the case for any hill, but just the shape of the hill we have in that location, it actually caused about a 12% wind speed reduction because the reading on location 4 is 88% of the original wind speed. Now, when we look at the east direction, 90 degrees, the hill there is taller, and what it does is that it causes a greater wind speed reduction of about 47%. And you can see that as location 3 records 53% of the original wind speed. So these findings tell us that, okay, from the west and from the east, the two hills are causing the wind speed to slow down by varying amounts. What does this actually do when the wind approaches the CBD buildings? So using those wind speed reduction factors, we ran simulations. So here is a result for if the wind is coming from the west again. Now, figure C shows that Cyclone Gabrielle is approaching the CBD buildings without accounting for the terrain factor. And you can see that upstream of the buildings, to the left of the buildings, we have that 21 meters per second velocity, very severe wind speeds. And what happens is that once the wind approaches the buildings, in some parts, the buildings shelter the wind speeds, so the magnitude gets mitigated. But in some regions, it gets accelerated closer to the waterfront, to the top of the plot. And what it really shows is that the wind environment in the CBD at parts is calmer, but in a lot of places it's actually getting worse. But that's not necessarily the real picture. So figure D shows the same simulation, but now we're accounting for that wind speed reduction factor. And you can see that not only is the magnitude of the wind speed approaching the buildings smaller, but that smaller magnitude actually influences the building slightly differently. We get fewer wind amplification regions where the flow accelerates. And in regions where it does accelerate, the magnitude is smaller. So really what we're seeing is a calmer wind environment. Now, this finding is even more pronounced when we look at the east direction because, again, the wind speed reduction factor was bigger, just because the hill was taller there. And figure F shows, again, the simulation of Cyclone Gabrielle without the terrain factor. Again, very severe wind speeds, as high as 75 kilometers an hour, even within the building configuration. But then when we apply the terrain factor, which would be the case in reality, figure E shows that it's actually a lot calmer than we think. So we're getting a lot of support from the terrain to actually shelter the winds around the CBD. We still get some regions of wind speed accelerating, but not to the same amount as our simulations would show without considering the terrain. So just to conclude this short story on Auckland's terrain and the wind speeds of Cyclone Gabrielle around it, we know that Auckland sits on very complex and diverse terrain which undoubtedly has an influence on any storm approaching the city. Just looking at one terrain feature from the east, we saw a 47% wind speed reduction. And from the west, we saw another wind speed reduction, albeit of a smaller amount. But nonetheless, using those ratios and those wind speed reduction factors, we saw that the CBD wind environment is a lot calmer than we thought, but it's a good finding to know that. However, just the setup of the buildings themselves can still cause the flow to accelerate, which can be worrisome. Thank you for listening. This was a short presentation, but I've been very excited to share it with you all. And I'd just like to thank all of my collaborators at NIWA and the University of Auckland and the RNC community. So that's it for me, and thank you.
Wonderful. Thank you so much, Muizz. Yeah, quite a startling contrast between the east and west wind there, and beautifully conveyed in that very colourful diagram. Thank you. So I'm delighted now to introduce our final speaker for today, who is our only master's student part of the program. Everyone you've heard from today has been a PhD student that has been studying for at least or approaching 3 years. But today I'd also like to introduce Eugene Kavale, who is a master's student from Te Herenga-Waka Victoria University of Wellington, and he will be presenting today on his project, Effective Monitoring to Support Dynamic Adaptive Pathways Planning. Over to you, Eugene.
Sweet, thank you, Jenny. Is that coming through all good? You can see my laser pointer too?
We can.
Perfect.
Looking great.
So I'm Eugene Kavale. I was supervised by the incredible Judy Lawrence and Rob Bell, without whom this would not have been possible. So I just did a 1-year master's. And disclaimer, it has been a couple years since I finished it, so I'm a bit rusty. And I haven't had much to do with it since because I randomly ended up in rural Wales afterwards. But luckily I had my old STARR Talks to refer back to, and my thesis as well, I suppose. So I was studying effective monitoring to support dynamic adaptive pathways planning. That fit into the coastal adaptation space of RNC, but it's actually quite related to that risks and hazard uncertainty theme we were discussing earlier. So the context for my research was long-term sea level rise is very uncertain. Long-term, I'm saying, if we look at 100 years away, 2.6 meters, 8.5 meters, we don't know. But the issue is local councils today are making decisions that, building infrastructure, whatever, that's going to last a long time and be subject to unknown levels of risk in future. So rather than trying to pick a future scenario and do our actions now based on that, what the DAP approach instead does is you come up with different pathways you could go down, so different actions you could take. So this is the advance of time as we go to the right. And a key aspect of DAP is to monitor ongoing increase to risk and to change what you are doing before you reach your adaptation threshold, which is the point of failure. So we don't want to get to this stage. So what we do is we develop, we are monitoring certain indicators. We have our early warning signals to say, all right, we're heading towards that adaptation threshold. And then at one point, we have to decide on what is our trigger, which is when we actually switch to a different action or pathway. And this hadn't really been done in New Zealand yet. The DAP approach was invented in the Netherlands roughly 10 years ago and has been adopted in a few places worldwide, but obviously in practice there are limited examples. So at the time of my thesis, it was just being implemented in New Zealand. So what I did is I had to discuss it with those implementing it, and the most advanced case study was in Hawke's Bay with their coastal hazard strategy. So the DAP process overall has quite a lot of steps, and monitoring is the final part of that, and they had just gotten onto that monitoring stage. So what I did is I interviewed different people involved in the strategy, which is council staff, mana whenua, and community. Those are all one-on-one interviews. And I should note, that was quite a difficulty with this research. I had just 1 year to do it, but people are busy, and it's very hard to talk to multiple people at once as well if they're busy. So that was probably my main issue. I listened in on some community workshops that were hosted by the strategy itself. So that was a multi-council affair so I listened in on that when they were developing their adaptation thresholds with the community. I also held an online regional council workshop. So that was me, my supervisors, and a few council members from around the country, just to discuss things basically, because like I say, people hadn't really done this monitoring yet. So as far as writing research about it, that was about all I could do, is discuss it with those who are going to do it and consider the practical element of actually doing it, and then compare this to what's already been published in the literature and a few case studies from around the world as well. And so the key findings I found, really there were two aspects of monitoring that I could discuss, which was the design of the signals and triggers themselves and what indicators you're using. And then there was actually implementing that system, because like I said, this is an ongoing system which is meant to last long term. So for signal and trigger design, so I should mention these criteria are sort of evolved from conversations with people, but also what was already existing in the literature. There was quite a big knowledge gap of, how do we do this? What barriers are we going to face? And there's a lot of them. And then how are we actually going to address those? So yeah, are our indicators relevant? Do they meaningfully signify a risk? What are we actually choosing to measure? And then can they be practically monitored by councils or other organizations? And then this data fed through. Will they actually give us that early warning to warn us about an adaptation threshold ahead of time? Because depending on the situation, you might need years, months or years in advance. Are they resolvable? Are they reliable and convincing enough that it's going to be okay, we have reached our trigger now? And as far as implementing it goes, can it actually be incorporated into monitoring functions? This notion of who's actually going to do this, how are we going to fit it into what we already do? Because like I say, people are busy, councils are busy, and that was a big issue that kept coming up, is how are we going to slot this all in? But they've already got enough on their minds. Is it sustainable enough that we can perform it in that long term? You're going to have staff turnover. Who's going to keep doing all this? And then accountability. We can have all the data, we can have everything there, but how we're going to make sure people actually act on those triggers. Because the reason we do this in the first place, the reason we're reversing this approach rather than depending on a projection and deciding, okay, this is what we're going to do now, it's more to say, what would be failure? How can we avoid getting to that stage? Because that's going to be costly. And that's what we're trying to avoid with this proactive approach, is just trying to minimize costs in the long term. So since then, like I say, that was a couple of years ago. A key document at the time I was writing it was the 2017 Coastal Hazards and Climate Change Guidance. But about a month ago, this one came out, and I was chuffed to see my name in there. This is roughly, from my thesis, a few times sprinkled throughout the document. And I have to thank, I don't think he's here, Aku from RNC as well, another PhD student. He's the one who actually pointed this out to me. But yeah, so I went through that a bit quicker than intended, but thank you. Thank you to RNC, my supervisors, and for attending my lightning STARR talk. And happy to answer any questions.
Thank you very much, Eugene, and congratulations. Are you calling us from Wales today?
No, I'm actually in Australia now, working in biosecurity.
Oh, very good. Well, thank you very much for your presentation. I've just popped a link in the chat to an article written by your supervisor, Judy Lawrence. She recently did a synthesis of 10 years of DAP in New Zealand. So if anybody wants some more information there, they can follow that link in the chat. But for now, I would like to hand over to you all for our next session, which will be the breakout rooms. And just before I send you all off into those different rooms, I'd love to introduce our 3 facilitators for those rooms. So for the Accelerating Resilience, that room will be facilitated by Caroline Augston from the University of Otago. Caroline's the director for the Centre of Sustainability and also a co-leader of the Resilience Challenges Rural Communities Research Program. So thank you very much, Caroline. For the Hazard, Risks and Uncertainty room, that will be facilitated by Andy Nicol from the University of Canterbury, and he is also the co-leader of our Earthquakes and Tsunami Research Program. Thank you, Andy. And then finally, in our Impact and Planning breakout session, that will be facilitated by Nick Craddock-Henry from GNS Science. And he is also the co-leader of the Resilience Challenges Planning, Policy and Governance Research Program. So thank you very much to my fellow facilitators today. I will open the rooms. You'll have half an hour for discussion, in which time the rooms will close, but feel free to come back to the main room at any time if there are any problems or questions for me. Thank you very much, everybody. I'd like to hand over now to the facilitators in each room just to give us a quick summary of what was discussed and some key things or key takeaways or really interesting things that you guys covered. So if I could start with Caroline, if you're online.
Kia ora. Yes, I'm here. Thank you so much, Jenny. And we had a really vibrant discussion. First of all, I just want to acknowledge both yourself, Jenny, and also all of the presenters for really handling some quite challenging tech issues, and you all did incredibly well, so well done. So our discussions around the 3 presentations that were in the Accelerating Resilience group were really interesting, and I think the key thing was that the researchers all demonstrated strong application of their work and really an ability to make a difference through the research work that they've been doing. So we had stakeholders from Department of Conservation, New Zealand Transport Agency and others who are really interested in the application of the work. So we discussed Lydia's work in quite a lot of detail about the tourism sector and how we can work to improve the resilience of tourists, and came up with some novel ideas around using social media to send messages about the reality of being in the backcountry where it's not all sunshine and clear skies. And that maybe we need a new campaign where we share our terrible images of mud and freezing weather and when things don't go as well as planned, because that might share the message that we need to be more considerate of bad weather and other things that could affect us in the backcountry. We also talked about the Swiss cheese model of resilience, where we need to make efforts across multiple channels to make change, and we can't just assume that it's going to happen from the grassroots or from regional or national levels. It needs to be a collective where we're really trying to work on resilience efforts across those scales. And so, yeah, Lydia shared the Swiss cheese model, which I totally agree with, which involves lots of work across those scales. That might be all we have time for, but it was a really interesting conversation, and thank you again to those 3 speakers for their wonderful presentations.
Wonderful. Thank you so much, Caroline. I'm really glad that those 3 talks produced some really stimulating discussion. And so thank you very much to our 3 presenters in that session. Manomita, Chanthujan, and I'm doing this from memory.
And Lydia.
And Lydia, yes, of course. Our next session was the Hazard, Risks and Uncertainty, facilitated by Andy Nicol. Andy, could you share your highlights from the chat?
Yeah, sure. So we had 4 speakers. Three of them were essentially gave presentations on this earthquake simulator model, and Annal talked a little bit about uncertainty and how we communicate those uncertainties, at least have a dialogue with, I guess, stakeholders and people of who have interests. We had the first discussion. We had our discussion in reverse order. So the first discussion from, or at least question, was around the uncertainties in the communication of those uncertainties, and the question was around, okay, do you ever have any people that say, no, I know there's uncertainties, just give me yes or no or an answer so that I can go away and use it. So that was kind of an interesting perspective. That I've had that similar response as well, and so it kind of raised the importance, I think, of understanding exactly what stakeholders want. Certainly in Annal's experience, they want to know about the uncertainties. That would be my perspective, but it certainly seems like there are other perspectives out there that we kind of need to work through and figure out what it is people actually want in the uncertainty space. So that was a great discussion. I think the other three speakers, if I can try and wrap them all together, they were basically dealing with the earthquake simulator and using the earthquake simulator to understand hazards. And a lot of our discussions centered on the very important question of when we have earthquakes on the subduction thrust, so say beneath Wellington, the subduction interface, what's going to happen in terms of other faults? How do we convert an understanding of those earthquakes into the hazard space? Is it going to increase the hazard? Is it going to reduce the hazard? And we had quite a nice discussion on multi-perils as well, around, okay, we know we've got complicated earthquakes. What does that mean for multi-perils? Does it mean we're going to get more landslides? Is the tsunami going to be bigger? Is there going to be a tsunami? So it kind of highlighted the fact that these guys have done an awesome job and they've made some really good progress, but we're still sitting here scratching our heads with quite a few questions about what's going to happen in the hazard and risk space. So it's kind of quite a nice lead into whatever might happen next. So anyway, well done, guys. Nice talks and good discussion.
Thank you so much, Andy. That's great to hear. And yes, congratulations to our students in that session. That was Jade Humphrey, Govinda Prasad Niroula, Mika Liao, and Annal Dhungana. Thank you all. And so finally, we've just got a couple minutes left. If I could hand over to Nick Craddock-Henry to provide a summary of the impacts and planning discussion. Nick.
Thanks, Jenny. Yeah, so we had presentations on a couple presentations on flooding in sort of rural and compounding flood risks, as well as the effects of wind on Auckland and Cyclone Gabrielle. And then unfortunately, Eugene wasn't able to join, but Eugene's sort of take on monitoring signals and triggers for dynamic adaptive policy pathways. It was a great discussion and just kind of reflecting on kind of three kind of main points. The first was the extent to which we have actually learned from the way resilient exposure to flood actually can enhance future preparedness. So if you do get a flood, then his model showed that you were actually able to the system was able to sort of learn from that. While that is great in a model, we talked about how in reality we don't necessarily learn or at least incorporate those lessons successfully. We talked a bit about Wairoa. I think the second thing that kind of struck me was that all of the presentations kind of took a bit of a systems perspective and that need to account for those interactions between different risks, but different responses as well. So Thomas talked a lot about, the sort of the cascading and compounding risks and the accumulation of risk within a system can lead to that kind of threshold being breached. But conversely, some sort of any investment in repair in that system can enhance future preparedness. And finally, the third sort of thing that we talked a bit about was, on that sort of systemic perspective, I think it was Muizz that said everything influences risk and adaptation, because we talked about the spatial footprint of Auckland and how actually it's the shape of buildings, the orientation of those buildings, and the terrain, how that in turn influences the exposure. But finally, it was that kind of
kind of relates to Annal's presentation as well, and as Andy pointed out, many of the other presentations, is the sort of dynamic and uncertain nature of current and future risk. There's a well-known paper, Stationarity is Dead, and that the future is highly uncertain, and trying to prepare for that, whether it is earthquakes or climate change, we do need better tools, better processes, and better ways, as Eugene pointed out, to actually account for the uncertainty and how we actually then connect that to decision making. So thanks to all of the presenters and to those that came along and asked great questions.
Wonderful. Thank you so much, Nick. That brings us to the end of today's session. Thank you all who have stayed online to the end. Students, I hope you got a lot out of it. You had wonderful presentations today. So I'd just like to acknowledge Caroline, Andy and Nick for my fellow facilitators today, and to our students, Manomita, Lydia, Chanthujan, Jade, Govinda, Mika, Annal, Thomas, Joshua, Muizz and Eugene. Those were 11 of over 120 students that RNC has supported or co-funded or fully funded over the last 10 years. And it's been really special to watch some of them progress through different degrees and end up being researchers for us and other institutions. And, you know, they're the researchers now and they're the researchers of the future. And so we've been really excited to be part of the early or the start of your careers, and we wish you all the best. Thank you everyone for coming today. There will be a recording of your presentations made available that I will edit out the technical glitches from, and I will share those with the people who are not able to make it today but still registered for the webinar. Thank you so much. I should finish out with a closing karakia, beg your pardon. So, ka whakairia te tapu, kia wātia ai te ara, kia turiki whakataha ai, kia turiki whakataha ai, haumie huie tai kie. Kia ora koutou, kia pai tō rā. Thank you, everyone.